You might have heard of two little particles called protons and electrons. You might even know that the proton has a positive charge and that the electron has a negative charge. And when these two particles are near each other, they attract each other because the rule opposites attract applies. But a better question is, how much? How much exactly do these two oppositely charged particles attract each other? If you don't understand what I mean by how much attraction, let's consider the following scenario. Okay, so let's say we have a car, toy car. We're holding on to this with a string, and this has a big magnet attached to the front. Okay, magnets have a north and a south pole. Sorry, I misspoke. This should be the north and this should be the south. Let's clarify that from the get-go. And then let's say we have another stationary magnet over here. Okay, positioned such that the north of the car's magnet aligns with the south of the stationary magnet, and that the south of the car's magnet aligns with the north of the stationary magnet. Okay, so just to clarify, this is the north and that is the south. Okay. I'd like to acknowledge that magnetic attraction is very different from electric attraction or electrostatic attraction, but the concept of attraction is still very similar. For now, though, we'll ignore any other differences, that may complicate this issue more. Okay, when we let go of the car, though, when we say let's cut the string, okay, and we remove it, this car is going to go flying towards that magnet until these two link up. Just like that. Let's just say that the car is right here, okay? Let's say it moved right there. Okay, so when we let go of the car, the two magnets link up, and then they stop moving. In a similar scenario, okay, let's say we switched out this magnet right here for a bigger magnet, a bigger and stronger magnet. Okay, so this one's going to be much bigger. Okay, we have our south pole right there and our north right there. Okay, we are holding onto the car, and when we let go, what's going to happen? Well, since we are using a stronger magnet, the strength of the magnetic pull between the car and the stationary magnet increases. As such, the car accelerates even faster towards this stationary magnet. So, much faster. That's the difference between the small magnet on the car and the big magnet. Now, the time it takes for this magnet to link up with the stationary magnet. That's the difference between the two scenarios. The strength of this pull is what we can call the degree of attraction. This doesn't exclusively apply to magnets, but also electric charges like in protons and electrons. So, attraction is equal to the strength of pull. Let me clear this out. Strength of pull. Okay? So when we say how much attraction, we are really asking how strong is the pull. Because attraction is essentially a pull which influences the motion of an object, attraction exerts a force and must be included in a comprehensive free body diagram. So now you might be thinking, okay, so we know what attraction is, but we still haven't answered our initial question of how much attraction. In other words, what factors influence the strength of the pull between two charges? Firstly, the magnitude of the force of attraction depends on the type of attraction we're talking about. In our initial example, we were talking about protons and electrons. In this case, we are dealing with something called electrostatic forces of attraction. I'll spell that out. Electrostatic. The factors that influence electrostatic attraction is expressed in an equation called Coulomb's law. Okay, and that looks a little something like this. Let's see, what can I do? I'm going to erase just a little bit some of this diagram. Okay, back here. So Coulomb's law is an equation, and it looks a little something like this. Fc, now I use the subscript C just to denote C for Coulomb, but you can use any subscript you want. You don't even have to use a subscript, but F, the force, is equal to K Q1 Q2 over R squared. Okay. Fc, as we mentioned before, is the electrostatic force exerted on two charged particles. Q1 is the magnitude of charge for one particle. Q2 is the magnitude of charge for another nearby particle. And R is the distance between both of them. K is a constant that takes the units from K1 times Q2 divided by R squared and converts them into force units. So let's take a moment to consider what K is. The value for K is 9 times 10 to the 9th, okay? But we just mentioned that it's going to take these silly units and convert them into force units, newtons. Q is measured in coulombs, and since we have C times C, essentially 2 coulombs multiplied by each other, we're going to have C squared on the top, and then R is measured in meters in SI units, so we're going to have meters squared on the bottom. So we're going to have Coulomb squared, meter squared, okay? Just considering Q1, Q2 over R squared, okay? What we have to do then with K is take these and use a little bit of dimensional analysis to convert them into newtons. So if we have C squared over M squared, okay, and we want newtons, what are we going to do? Well, we can multiply this by meters squared over Coulomb squared, and then multiply this by newtons, so that these will cancel out with these, and these will cancel out with these, and so you're left with just newtons. And what do you know? This conversion factor right here, oh, you can't see that, this conversion factor right here is exactly what the units are for K. The units for K are Newton meters squared per Coulomb squared. Okay? And that'll be pretty important because in some of the problems, you'll see that Q1, Q2, or R is not always given in these units. And it's important that when we're calculating the force, that those units actually cancel out. Okay. Instead of relying on the strength of magnets, electrostatic forces depend on the magnitude of the charge of both particles, as well as the distance between them. So that essentially is Q1, Q2, and R. Okay, so now let's go back and address our initial question. How much attraction exists between a single proton and a single electron? For this problem, let's just say that they are 1 centimeter apart. So now I'm going to clear out some of this. Okay, and I'm going to keep Coulomb's law up there because we are going to need it. Okay, so let's draw just a little proton right here and a little electron right here. And let's say that this distance right here is 1 centimeter. Okay, and I'm just going to use 2 sig figs. First, we realize that we are dealing with electrostatic forces and need to know Coulomb's law right here. Okay? Next, we need the charges of the two particles in question. Since we're dealing with a proton and an electron, which have charges of equal magnitude, Q1 and Q2 are both equal to 1.60 times 10 to the negative 19th coulombs. That's just the charge of a proton and an electron. So Q1 equals 1.60 times 10 to the negative 19th coulombs. Q2 also equals 1.60 times 10 to the negative 19th coulombs. If you didn't already know, there are tons of resources online that'll give you this number. If you just look up charge of proton or charge of electron, you can get that. Finally, we have to convert the distance to meters. So we were given 1.0 centimeters, but we have to convert it into meters so that when we plug it into the equation, the units here will cancel out with the units in the constant k. Okay, let's get rid of those and then do a little bit of dimensional analysis. So the conversion factor from centimeters, there are 100 centimeters in 1 meter. So there's our conversion factor, and that is going to equal 0.010 meters. Okay, and that right there is R. Now we enter these values into a calculator and consider sig figs and box our final answer. So FC should equal 2.3 times 10 to the negative 24th newtons. And here is how much attraction exists between a proton and an electron that are 1 centimeter apart. Okay, so let's just do one more problem for practice. Let's just erase all this. Okay, and I'm going to need an image for this. So, just going to bring in this one right here. Here's the question. Calculate the electrostatic force between a charge of 5.0 microcoulombs and a charge of 2.5 microcoulombs, that is 2.0 millimeters away. In what direction do the two particles move relative to each other? Okay, so typically when you're trying to solve for the electrostatic force, the problem will tell you the charges of the particles in microcoulombs. That's just because 1 coulomb is actually very, very large. So typically microcoulombs are going to be more reasonable when you're trying to find the force between two microscopic particles, which is typically what's going to generate these charges. Since Coulomb's law requires Q1 and Q2 to be in coulombs, okay, right here coulombs need to cancel with the K units. We need to know the conversion factor from microcoulombs to coulombs. What helps me remember the conversion factor is that micro starts with an M, just like a million. Everyone should know what a million looks like. Okay, this is a million. Here I'm going to write it in scientific notation, which is just 10 to the 6th, and then take the reciprocal of it, 1 over 10 to the 6th. If you know that micro is a prefix that indicates something very small, intuitively you can figure out that there should be lots of microcoulombs, lots of small stuff, in 1 coulomb, one very big thing. So you can deduce that there are 10 to the 6th microcoulombs in 1 coulomb, and there's our conversion factor. Okay, so let's take 5.0 microcoulombs and convert that to coulombs. And I'm not going to do any math here, just simply put, it's just going to be 5.0 times 10 to the negative 6th coulombs. And for 2.5 microcoulombs, you can kind of infer the same thing. It's just going to be 2.5 times 10 to the negative 6th coulombs. Okay? Finally, we also have to convert millimeters to meters, okay? Because we were given something in millimeters, and we need those to cancel out with the meters in K. So 2.0 millimeters. I'm going to have to clear up a little bit of space. just take off this row right here, and let's do this one. Okay, so 2.0 millimeters